Hello, this is chapter on the image segmentation. In previous chapter, we covered the image feature detection and matching. So feature was, we said, is more like interesting points. So something, oh, that this is significant. This may lead us to some discovery of the object or some component of the picture so that we can understand the whole picture. That's the purpose of computer vision. So the feature, it was very small area or very simple components, usually called the local objects. So what we were interested in or we were looking for was that the little bit of a corner or like that, and we want to have what's the edge. So from here, checking, oh, here's an edge, here is an edge that's separating these places and that place, whatever that is. Then, so there's a one corner and then edge. Then the general area, well, there's nothing, or the inside is all same, whether it is inside of the sky or is inside of a certain rooftop, is all same. So this is continuation of the same property. So we have been detecting something important. Now that with those idea that, okay, we they kind of detected, or we marked here those corner points and some lines identified and the general area identified, then we have to group it. This is one group, this is another group, this is another group, so that we can identify it as a separate unit or some kind of an object unit that we want to discover. So that's the whole purpose of computer vision, where that we want to understand what is in the picture. So again, human beings can do this one very naturally, without thinking, without worrying about it. But turn out to be that it's that we have been trained to understand the picture over the years, several years actually. So when we are a baby, then we don't know what's going on. Everything is just flashing around, but I have no idea what it is. On the other hand, as you grow up, start seeing and identifying familiar faces like your mother or your parents or your friends or something to eat, this kind of thing. So anyway, segmentation is that in this picture, for example, in here, in this whole picture, we say, aha, there's a one similar idea or the blob, and another one that obviously is a car, and this well, the white line is some kind of a road sign, and this are the grassy area, trees, those kind of identifications. So we, in a way, classify into groups, subgroups. That subgroup is called the segments. So whole picture is, in a sense, separated out into small section. That's what the segment is, what we are doing. Then this example shows that there's one nice picture. Human beings, again, that can easily see there the horse, I think it's a horse, that maybe it's a mother horse and the baby horse. Very easily find it, but machine does have just a pixel value, but with this segmentation, so before we have features, here's a line, here's that, and here's the lines, and this is the same area, this is the same area. Based on that kind of information, we started to classify one group separated from the other. Because there was a certain lines in between here, we say, aha, this is not one object, but two objects. And sooner or later, by the shape of this head and maybe color and this the long, the stretched one, then what we call leg, and the tail, that we may be able to identify what it is, what kind of object it is. Is it a living thing? Yeah, it's an animal. Then what? It is a horse, cow, or a goat, things like that. So that's how we are getting into closer to the fully understanding our picture. So once the object is detected, we know that there's some object, then its property and the relative of the location in the image is calculated and laid into separate segments. So in a way, internally, you are making subsections of the picture elements. So here again, same idea I have been talking about. So Zelinsky's book talks chapter 5 of the Zelinsky's book, talking about this segmentation. Segmentation is also a very important subject, and it's one step further into the identification. Well, everything is important, and feature is a good start. Then the segmentation is the next very promising or important step. So here the images can be, in other words, that each picture you have the captured and cleaned up has a lot of those subjects in there. We want to know what's in there. So what's in there is actually our segmentation process and eventually identifying the steps. So here some kind of mountains. So you see that those the line separating those borders or edges, and then this is an area or the region, and there's a points, and here's certain points like that. So the feature we have been detecting in previous chapters coverage is all used up. Of course, it should be all stored in the programming component in the memory, and using this information, we started separating it out. Starting point, of course, is a points, and then lines and areas. So the point is 0 dimension, line or edge. That's I said the edge is the more of general the shape of the lines, and the straight line or linear line is a straight line. So that is a special case of the edge, and of course the area, so two-dimensional. All those 0 dimension, 1 dimension, 2-dimensional component being detected from feature detection. Now that being used to separating our different regions, so different subsegments. So this is the area, this is a same group. So in a way that we are separating it out. Usually it's called analytic because we are tearing apart, or it is a bottom up approach because we are concerned about the small things, the individual element, and start grouping together and say, aha, this is one group and this is another group. Those are separating out from small things to larger scale. So it's very hard to do top down because we say, oh, this whole thing, and then chunk it out into small the right away on here, but rather it may say that individual pixel and this guy's looks all same, this is the same, this is the same, and from this segmentation segments, we get the data collected for the next stage of the computer vision, that is understanding the image. So by going through those the edge detection and of course the pointer direction area separation of region, those area identification, we got one step closer to the image understanding. Then there's in the goal set, the goal of the segment is group together in similar looking pixels for the efficiency of processing. So we are saying, well, this is one group, this is another group, this is another group, this is another group, like that. So in that process, we may be working on smaller pieces. So of course that actual picture doesn't look like it is kind of a mosaic of the pieces or tiled up, but we say that each unit, instead of a single dot as one pixel, we say, oh, one groove of this, one shape of the square, and a little bit different one. Those chunks are like one pixel that the composing or that constituting the one object or one segment. So sometimes that's called the superpixel. Pixel, of course, is one dot, but we want to grouping the X number of dots and then use that on as a single unit. So it's much like a region sometimes, or when we're talking about the edge components are actually superpixels. Then, so it is always a bottom-up process. So we go from small pieces, individual the pixel, to larger ones gather together, and then group together until we cannot grow any further. Like in here, you grow any further because that's stopped by some edge or some kind of borderline. So if you go to this publication, there is a pretty good introduction and the techniques for segmentation. If you are interested in researches, then this paper is pretty good. This is the original link wasn't good, but this link is working. So why don't you go ahead and look at that if you are interested in. Then it is unsupervised. It's about the learning wise that this one doesn't have any previous knowledge. That's unsupervised. So it's a machine learning wise, it's a little primitive. So of course these days there are the smarter way of the searching to or the making segmentation. So again, the goal of segmentation is into separating image into coherent, it's understandable objects. Coherent is grouped together, oneness. So in a way, this is a one object. That's some kind of boar, some kind of a wild cow, and here's another object, some object, and then here is some the patch of grass, and then there's a sky. Well, much like that also. By those separation of the lines, of the edges, that you can get some segmentations being created. And then here is the another picture of a two-person and some the wheels and a roof like that one. That can be by just going through those edge detection and minimizing. So that's thinning those lines instead of multiple the pixels, make a single pixel lines. That way, then we got the much nicer the silhouette of the human beings, and based on certain pattern. Of course, right now that we have some semicircle, and this is half circle here, and there is some bulb here, and there's a long one here, and there is another one. This one does not give us the idea of an object of a human yet, but soon it will be because of the head part and a body part and the lower part, the leg part and the toe part. That can be all fitting into whatever model we have for identifying the objects. So in here, that segmentation is a very progressed next step of the object identification. So this can be by now that it can be even top down maybe, but still we got to begin. What I'm saying is that creating into the segmentation, one segment, another segment, another segment, another segment, is definitely bottom up the steps or the process. But from there, we started getting some kind of idea. You know, there are too many objects in here, so we may have to say, oh, this is a not that simple situation, and we may have to have many of the objects, small objects, whatever that is, and each object come to be that is not simple circle, simple square, not simple star, but there's a long oval thing, and then there's some kind of sticking out things, and there's X numbers, and one end there's another sticking out. Then say, oh, that's gotta be some kind of animals. So you can get those patterns. So the identification of those blobs or segments into objects can be again top down, going from top to down, but still it can be bottom up. So here's one piece I found. There's another piece I found about those long one in the bottom part, and there's above that there's a longer the oval that may be something else. Then there's another oval we are expecting, and there's a slender oval down there. What is that? Well, actually, natural objects that rarely there is a straight line, isn't it true? So even this picture, you see that almost everything is a non-straight line. But here we have a straight line, here and here, here. Why? Because that's a man-made. So human beings usually give some straight lines or simple linear edges, but nature typically doesn't give you the straight line, but rather some kind of a curvature. So this is curves like that. Then sooner or later that we got to be curious about what is this, and then what is this? Is another human? Well, it looks like a human, isn't it? But turn out to be it's not. There's some wheels, and there's another some kind of the decoration or some container that hanging from those rooftop. So in a way that identifying those objects is pretty much the difficult task. That's why we need a lot of AI in modern days. Old days, or even these days, that we get a lot of picture from another planet, another the universe, the part, not solar system, but another place, and we don't know what it is. We have never seen it. Nobody ever been there. So the picture is new, and try to figure it out what it is. And then that is kind of interesting, but also very difficult job. So in understanding those objects, we just had right now, initially there was features. So that includes the corner, and then edge, and the region. So this corner, the points, and the edges, and then regions. But from here, we do segment. So we separate out the whole picture is separated out into subsection segmentation. Then we got to understand, we start getting understanding. The one hard part of the human, in this identification is that what we have originally in the world is 3D. But we must have that on into 2D. All the pictures are 2D, even if that is a stereo pictures, but it's a little difficult to represent it. So, and the camera so far is always 2D. So from there's a lot of perception problem. So even whatever you see it from the screen and whatever you see actually in your mind may be different, and what you are identifying may be different, and how machine can do. So to do that, remember, if you remember that on the first day of this class, I had a series of the examples, and in the PowerPoint, that all the illusions or mistaken identity. I did it just for the fun, but at the same time, that is also a very important clue in identifying. So it was not just for the fun, but it is a very serious subjects to study when you are doing those illusion. But anyway, looking at that, the Gestalt school, that is that the human psychology makes some kind of a different perception. The Gestalt is a shape in German, and the shape based. So our eyes or our brain will they make a lot of judgment based on certain shape. And well, for example, the very simple idea about this is a happy face. Happy face. Exactly the same thing, but if I had that, then it's the same face, but this is a happy, this is a gloom, sad, who knows. So just a little curve differences, just opposite, and it makes so much differences. Can machine handle those? Well, we have to make our machine also handle that. So the grouping of how those the individual components are grouped together makes kind of a different factor, an important factor in making understanding. So this is one good example of illusion we had. There's a name for this, but anyway, so we have those two lines in originally, but everybody thinks this is much longer and this is much shorter. The only difference is that this direction of those end branches. So this one goes inside, this one goes outside. So from here, even if we see nothing moving, but we feel like something is going on. In a way, this one is stretching out. On the other hand, then this one is squeezing in. This one is squeezing in. So we say that this is some of shrinking, this is some of expanding, and our psychology tells us that, oh yeah, this got to be longer. That's even if that when you measure end to end from here to here and end to end here is exactly the same length. I've been showing that one in the first day demonstration of illusions. So, but same thing happens here. This is all of the psychology we are talking about. In here, what you see here is that this shape is pretty much like those game, the face. I don't know whether you remember. There's a thing called Pac-Man. So Pac-Man is a kind of game pretty popular for quite a while. That's gobbling, and moving around, eating those dots. Anyway, that kind of face is just a simple face, and because of the shape that we feel like this is a smiling or the greedy. Who knows? There gotta be some eye here. So anyway, but important thing is that this is identical. These are the identical Pac-Man shape. But because of those direction, our eye or the eyes see just this have the partial line and the partial line. But because our eyes keep moving, we automatically connect those empty space into the line. Same thing, it goes in here, so it connects that, and this connects that. So it's a wonderful triangle there. Even if it's not there, but it is looks like that we feel like it's a triangle. Then this one we see some kind of it doesn't connect to the end, but still we see that there is some kind of the rectangle showing. Then here, that by this way, the contour-wise, these are two same keys, but we definitely see because of this, then this is situated under this key, isn't it? Everybody we thinks so. That way, what we are having is that we see the three-dimensional perception. Then this is even more interesting. That it is just kind of this cone showing here in a certain way, but we clearly see, very obviously see, there's a bulb with sticking out the spikes. It's like the coronavirus spike here. Then this one is also that configuration. We don't know what it is, but we may be expecting that this one goes in here. So it may be the long snake or some drag on the water. So many parts missing, but our brain is connecting those missing part, missing link, we can take care of. That's a school. Then here's a perceptual reality. I just added some more. So foresight and concept. Oh, by the way, if you are interested, actually I have the PDF version of the book. That's the newest one is the 2012 edition, and very useful, and some cases is very popular book, so you can use that if you wish. I mean, you can read that, so I'll make this one available. But again, these dots are arranged in certain way and make our eyes get a 3D perceptions. The main trick, of course, is that the top one is a much darker and a clear circle. On the other hand, this one is a little bit slanted or elliptical, and this got the faint around it. And this kind of cue of those intensity gives us clue about this the three-dimensional the perception. So it is a perception or reality. So 3D objects like that, even if that we have much less points, we still get it. And then this one, instead of a dots, we have a squares with a certain the texture inside. Still, we see that one. Then occlusion is more like that. We see from with this very partial the shapes in here. Because of this arrangements of corner, we somehow see there is something missing or covering on top of it. So we can kind of reconstruct this kind of some kind of objects or those structure that is obscuring, that is the hiding those main unit. So those dark part is that's the main thing on the back, but there's something. It's much like there's some kind of a shape in here, but there is another structure or vine. The vine is blocking the shape, and same thing goes in here with those missing portions. So a lot of missing dots that human can connect, and they can human can actually generate those understanding. Here is something. This is usually in a quiz. I'm sure whether you can understand this or not, but there's a hidden picture. What do you see? Then when you look very carefully, then we say, aha, there's a dog. There's a dog, more like those spotted one. And then even if there are so much part is missing, but by those shades, some of those clue, and some kind of a thing, human eyes will reconstruct or make a connection to this missing dots, and bring the total picture into understanding of certain figures. We talked about in some weeks back, there's the technique called relaxation. So relaxation is the way that we have a little portion of the lines, but we somehow connect that one. The concept is very similar. So what we do is that we are keep searching, just in a hope of finding some kind of a connecting points. So if we have the one dots here and the one that's there, then we are somehow following through those lines. So even if this the 3 points are just not related maybe, but our eyes, our mind will follow through and go to see if there's anything to connect. Here we have just a little dots, then we want to connect this with the expectation of a certain curve or some kind of shape. So that's why that this picture isn't that easy to recognize that as a dog, but it takes some imagination, so sometimes used for IQ tests. So in a way, those dots are in a series, and it gets into the vector. the connection goes in here. So that's an interesting way, in a way that the algorithm of computer vision, many of them are actually devised or based on human perception. So we say, how can we see a dog from here? Okay, we are connecting the dots. Then why not? The connecting the dot means that there is a certain sequence of dots. So let it be some kind of motions, and that eventually keep going on and hit some kind of a next connection point. Then even if there are a lot of missing points, people will say, okay, this is one big line. We were talking about Gestalt theory, that is how human mind or brain understands those the objects or what they see based on the shape. So the Gestalt, again, it means a shape in German. So we say here, if we have this kind of arrangement, then there's no clue about what is this. All we see is these 6 dots equally spaced. But once we just move around just a little bit, then there's a longer gap than this one and a longer gap than this one. Then we say, aha, there are 3 groups. Because of proximity, they are closer, so they are same in the group. So when we are identifying or we are searching for segments, whole area, then we got to find those subsection. Remember, there's a pixel and a superpixel. So this is, in a sense, a superpixel. How they are arranged, and do they belong to same group or not? That kind of a judgment can be done by some kind of arrangement shape. So here, same 6 dots, but 2 are dark and the other one is not filled, they are light. Then we say, there's one group, and even if these 2 guys back there is not the closer, but we see they are similar. They are having same property. So we tend to make this one and this one as the same group. This is another separate group. And same thing goes in here, similarity, that is a different shape. This one has just the filling in, that kind of property or attribute of the superpixel. Here, shape of the superpixel is that these 2 definitely, well, actually the same thing, except that this is a different direction. If it's a circular one, then one way or other, there's no distinction. But because of the this oblong or the elliptical, so it can be the long axis be vertical or horizontal, so it makes difference. And here there's a common face, that is that we put on arrow. Arrow by definition makes a direction or vector. So because that says always going down, this one going up, this one going down, again, because of those little help that we see that these two as a one group, their proximity plus then the fate of this direction is same. These are different, so 2 different ones, they are in the same group. Then by having some boundary being circled around. So just like the no grouping whatsoever in the first example, but by circling like that, then we know that these are the common regions. These are separate and don't belong to anywhere. That kind of the distinction we have. Here, again, that we are grouping the similar thing or different. It's we are same side or not. That similarity or the segment-wise is belonging to us or not, is that much like this one parallel. So we have, if we separate out those the 6 strands and all over the place, still we see that these are the same pattern of a parallel, and this one different pattern, this one different parallel, and the pattern, and gives idea about this is the same group. Then this one is not parallel, but say is symmetric. So we see the down in here, then we see left and right is all same manner. We have I cannot draw a straight line in there. So here the left and right is the same, and the same thing goes here. By the way, when any organisms, like I said, even small bacteria or some worm or the insects and human beings, then supposed to be symmetric, not perfectly symmetric, but we always has a symmetry in the center, two eyes there, eyebrows here, nose is in the middle, but those holes are symmetric, and the mouth here. So we always, when organisms are developing, they are doing somehow those symmetric operation, and very often they are built from outside and meet together. So at the birth, so in a way that is the natural way. There got to be some reason for this symmetry and many explanations that exist, as I understand. But important thing is that the symmetry is important part of a same pattern, and the continuity. So we have a connected they are. That one will be symmetric, and then here closure. So once we have, then it's inside and outside, inside and outside. So in here you can separate out the whole picture into three areas: 1, 2, and the rest of them of the 3. That kind of the understanding, and that kind of idea gives a clue to the finding the region from the pixel and from the feature detection. Another grouping. This is another interesting the idea about the grouping. This one I didn't know what it is, but I read the book here, the chapter 9 about Forsyth and the Ponce. This is the elevator button of the computer science building in UC Berkeley. So this is a button, this is an elevator button. You push it and it goes to the 3rd floor, the 6th floor. Then people had been complaining that, oh, I thought it is a 3rd floor, so I pressed this and it turned out to be I'm coming to. Then sometimes I say, oh, I pressed this one expecting it's a 2, but it's turned out to be 1. So it's confusing. Of course, this one, by the time it is at the border, you may say, oh, this button is for 3 maybe, but it's not enough. So often people got the wrong flow very easily and they got complaining. Some little less intelligent person designed this button. So there was one student who said, okay, I got a solution. What he did was that he actually put some patch around in here, patch around in here. So here, 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 here. Then are there any mistake? Very clear, isn't it? So you press this one for the 2 because it's all grouping. Nobody will expect this one for the 3. Nobody will expect this button for 6. That kind of association or grouping is another important part of the segmentation. There's so much about the psychology we are doing. This one somehow that I repeat that this one I'll just go over. So it's intuitive, but also very difficult into the algorithm. Translating into algorithm isn't that easy. Nevertheless, that from this kind of human understanding of our observation of our human behavior, that people are solving the situation or the problem, how to make this one work properly. So what it is that the most common segmentation algorithm is that pixel values. Luckily, there's RGB. So all those guys. First of all, this one is very homogeneous. So red is 3, green is 12, blue is 2. So it's mostly green, but there is a little bit of red and blue equal amount. Actually, red and blue together, that one is called magenta. So little purplish green, that's what it is. Then this one is 100% green, and this one is very much green, and this is more of a white. You see that if RGB value are balanced, they're close to near to each other, then it is the white color. When it is all 1, 1, 1, then it will be dark. Or 0, 0, 0 is completely black. Otherwise, it's 1, 1, 1 or 255, 255 all, then it's completely white. Otherwise, this one less of green and less of a little less of blue. So this one is a little greenish, little reddish, the white. That's how it goes. So on. So you have RGB of 3 primary color axis, and you can, based on those pixel values of each color component, actually in typical the graphics, that we call this one as a plane. So spacecraft also has that. So what they do is that they are taking picture for red with the red filter and the green filter and the blue filter. So they are making exactly the same dimension, physical dimension, but with the same the same sizes, but different color combination. So the red component wise, what is intensity, green and blue. That's done by filters. So if we have those separation being created, I mean they collected, then yeah, you can, depending on the value of red, green, blue, we can group those colors together. So for example, in here, this one has a pretty big red, but not much of green. So there's it doesn't have that, but this one has a pretty big green, and the closer to red and blue, not much. So each of those points depends on those red, green, blue, like that, and that we can plot them, and we say, okay, these two are same. So in a way, we are grouping these two together, and this one maybe not. They are all separated out, but these things are different. So we can make a separation of a different group, but these two are much closer than this one. So that's somewhere around in here. So you can classify by pixel values. Then the very important concept or techniques is K-means clustering. So this one is bread and butter, very often used in the deep learning and machine learning and deep learning. So K-means clustering is that it has very similar to our previous remember that we talked about eigenvalue, eigenvector. So that's more of a property. In other words, that each pixel or each group of those picture component has so many components, especially if it is one chunk of the segment. Then it may be color issues or intensity issues, texture issues, and some contamination, or some different depth issues. So there are so many issues in here. But anyhow, but from the collected data, all we can do is that just essential the properties. So that's our principal component analysis, more like that one. So K-means clustering is frequently done with a PCA type of the statistical analysis, and this gives in a way that in a given picture how many different components that can be clustered. So the clustering being done as by statistical analysis, and we have the RGB factor plus X and Y value. That is more of a location from the center. So not only RGB, but we also have a proximity of pixels that gives more data. So use those data, and you can make all those 5 generation or 5 the dimension or 5 factors will give more of the information that will be helpful in understanding which one is the right factors. So in here, this one, this segment, for example, can be one part on this red, green, blue, and plus the location of X and Y. It can be detected. So K-means for segment is the frequently used and very simple method, and using some statistical the analysis, it can be done pretty easily. But there are sometimes that some problem, that is, it takes so much main memory because there's so much of a calculation to do, and then we don't know what would be K. In other words, in a given picture, how many clusters do we expect? So K mean is that we expect, if it is a 5 mean, so 5, then we expect only 5. Then there may be these two are very distinct, but we in this technique, we will only identify 5 and no more. So that's not enough. So that's the little hard part. And you begin with where to start here, starting from here, that initialization or starting point, and how do you make those assumptions, then makes a big difference in terms of the decisions. And when there's something that's outliers, that outlier is one value that is off the limit and really exceptional, then it can give you so much about because it's a statistics, you're calculating, so one number like that. So in a way that this one, sorry that I made this a little bit of messy, but this is dots and the dots and maybe this dots, but by calculating somehow that it can cause this one very much like that as one group, this one as one group, and this one maybe as one group. So sensitivity to outliers is a difficult part, and so frequently what they do is that they are studying or they're checking the data, and anything that's outlier, there's a standard deviation. We have those normal distribution, and then the value that is like 2 standard deviation away, 3 standard deviation away. Then we just remove it, ignore it, and recalculate. Then this one is separated out, and then they just use this two very nice clustering. And the spherical cluster means that it is only spatial. So the other, that if go around it, then can be. But what if that we have a cluster somehow is in linear form? Then it doesn't find it, because it thinks because of too much of a dispersion, too much of a distances, they may ignore, or they will say that this is too separate, these two are too far away, so we don't want to put into the same segment like that. And then mean shift, the clustering, that is that then okay, anyway we can do this one better job. One improved method is a mean shift. In other words, that we don't say this is we say it's the center of the whole thing. But what if that we move, or we try out different starting point? Say that in previously starting point makes the differences. So in the landscape 1, then we have there's a separation, 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 and this one, in another picture, that we have a separated groups that can be separated as segments. So the mean shifter is that it is moving. When we see from this end, it may be from some angle, it may be difficult to detect those exact the separation. But you go around this center, the mean is shifting, then maybe you can be able to find the best separation. And so actually, mean shift algorithm is one of those sample example in the mean shift in the our Gig for Gig, the OpenCV Python samples. So maybe we got a chance, then we'll work on it. So in here, that the mean shifter is the 6 mode or local maxima. So mode is that in statistics that there's a mean, that is the average, and then median, that is all the value arranged from largest to the smallest, or the smallest to the largest, and the one in the middle. Remember, we said median. Then mode is that what is the most frequent one. So you draw this histogram, and whatever the value that is highest or largest value. So using that the mode values, that you can generate you can identify those values. So within that, what is most frequent part and what is the most frequent color. So you have a segment, many segments, and plot their the most frequent or most abundant color combination, and you make a certain pattern shown like that. The LUV color value is the different color model, but we don't have to worry about that. And so mean shift is you are moving, you're shifting. So when this is the location, or the first the starting point, then it's a little hard to see where is the best cluster. So we are moving a little bit center of mass. In other words, in here we have we started any location artificially. Then we see that the center of gravity means that the distribution of those dots, and what is is heavy. So you calculate those value of left and right, and those the x and horizontal and the vertical values. Then say, aha, the averaging. This one is a little too much. So when we calculate based on what is the distribution part, then from original one in here, we will say, oh, this is more like a center. Of course, in the circle is not the center. Then, okay, let's start it again. And then, so we move that our mean shift as over here to the new center. Then, so we move that and then recalculate it. Then, still there are more dots. So, okay, we thought that moving from here to here seemed to be a better idea, but turned out to be it's better that we got to keep going, because this is heavy. Heavy means more concentration of the units. So we do that. So we have that moved. Then we say that recalculate, and still a little bit off. So you change that and then move that. And then now that what is the new value? Oh, it's right there. So what it means is that we say we found the real center of gravity, and that's averaging, and that's the center of those segments. So across all points in the attraction basin of a mode. So the attraction basin means that the area, the trajectory, or those path leading to the same mode. So here, from here, then we see which value is the same as this one. remember there's a mode, most frequent value. From here, most frequent value, and there is a center of that. So in a way that we are following through, and with the mean shifting, that where is the center of gravity. So its idea is this way. Initially, I randomly chose any places, and this is our concentration, suppose. So we have, this is a center, I thought, but because there are more values, so if you average it out, then average over the horizontal and the vertical. So this one, location, then, oh, that this is heavy on this side because of those abundance. So the average may go on around in here. And then we are making the shifted mean. And then with the shifted mean, you can going through the same, the real center of everything clustered together. That way we can easily, or not easily, but we can frequently find the idealistic location of the center of those regions. So the in here that not only we are using the color value and the gradients or the direction, and the texture is sometimes useful. So here there's a certain texture, there's a pattern. There's a pattern like that. So using those values, then we are just calculating those multidimensional the data into single value, and then they put into the plotting into the dot with the color combination of which one is the highest, which one lowest. So this peak is here. This peak is I'm sorry, yeah, this peak is here, and then this peak is here, and the other peaks are here, like that. So in a way that we can, from this picture, that the center of the location of the gravity is somewhere around in here, This is where all the interesting objects are found. So this mean shift segment is a very useful technique. And by moving from here, that we say this is there are more interesting objects than this one, don't you think? I mean, here in here that is more interesting than this one. So we will move our viewpoint toward here. Then there we got enough of those on the balanced the amount of. We may want to go even more. But we don't want to miss this one. We don't want to miss this one. Then most promising area is around in here. So we are moving our shift, the mean value. Same thing here. There's something in here. So we say instead of seeing this way, let's see from around this way. So that way we have an even spread of interesting segments of the subjects also of those picture. Then this on the similar idea that we say that this one has something here, something here, something here. So we would like to move around, remember? So if we come out with this one as center, we got balanced on the left and the right side. And then this one has a more of this one, there's something and there's some mountains, but we want to have this one given kind of a going back, and then we see a more balanced view of the scene. So that kind of idea is given for the segmentation. And there are many pictures like that. So it's just moving. So from one point to another point, one point to the another point. But this one give the same the picture, but with the edge detection. And then with a different kind of weighing, so this dots become smaller, so that all those objects will have a balanced distribution. Same thing goes in here. The two are almost the same, but this one gets a little farther away and balancing the picture together. So mean shift. So we have seen then k-means. That's you set a maximum number of segments, and based on that you started separating or classifying each pixel to one group, another group. The mean shift is that the seeing where is the center of those best discovery of different segmentation, or the better yet, how to separate different segments most efficiently by moving the viewpoints or mean values. So that's an awesome spherical curve. It doesn't have to be the all centered around. It can be generally spread. Still, we can find the right one. And the single parameter, the window size, is only the one that to work with, and finds a variable number of modes. So you can use different factors, and there's some outliers doesn't affect those decisions too much. So that's good, but bad thing is that if a window size is not properly decided or chosen, then your result may not be good. And again, it's very expensive for calculating so much of us shifting around, and it takes long. And when the many feature space or the multiple features together, then again calculating is very difficult, and proper scaling is a little bit of a challenge, like that one. So the images, now that we are interested in knowing the relationship, how they are related. So here's the center here, and from there, what is there, what is there. So like those shifting mean shifting is pretty useful, that and where there is really the center, we are finding right center, because of remember this, we have a symmetry. So they are symmetric from left to the right. So from there, from this end, there's what's in there, what is there, what is there. Well, if necessary, we can have a further expand those contents. So this tail part, we can give another area of the interesting subjects, like that. And this one gets a front part of the tiger pictures. So the image has a connection of components, and that components has a relative position, left of and farther away. This is a back of and the front of. That kind of relationship can be specified for each component. So we create those pixel value, different pixel value being connected. They are generating into those graph. Graph is nothing but the point connected by line. So we have those different pixel values being connected, and edge between pair of pixels. That is how they are related. So this chunk and this chunk of pixels, how they are related, and this left of, right of, and then if necessary, then by similarity of those pixel values, we can classify as same or different. So this is a segments of just more like a modeling a given picture, and we have A, B, C, those are points. So sometimes the sum of them is a one unit. This is a one unit. This may be another unit, and this one may be another unit, and this is a separate unit. This may be something not belonging to one segment. This tiger is one segment, and then it's more like the tiger here is more of a body part, and then power part, tail part maybe, and this one is on the background pictures, like that. So you can separate out this picture, the tigers part one on part, as a separate units, and you can model the shape of individual the picture into separate segments. Then if the one segment is overlapping, then we say that, okay, that obviously that in here, this background, and this tiger part is somehow overlapping, then we separate it out first and see what happens later. So in a way, the all connected part is one, and anything left by that will be the other one. It's a background. And here, and then affinity is how close they are. So this one is Gaussian color. Remember, there's one of twice of the standard deviation, then E2 and the distribution. So summation like that one. So there's how the one pixel to another pixel, those differences are and how they are distributed. So by looking at that, how much of those the differences, the distances are observed, you can get those the closeness or farther awayness from each. So when it is a very small standard deviation, then you're grouping only nearby one. If it's a very large one, then it's just far away points, group large one. So in here, you're just grouping the one within certain range. It's much more like a normal distribution. I don't know whether you are familiar with, but the values close by will be in one group. Anything like one standard deviation and there's two standard deviation away, and they are in separate group. So these guys have X and Y value-wise a similar group, and then this one has cluster that's away from each other. So we have 4 elements here, like those the tiles, and we are creating the 4 different groups of this cluster. So in multivariate statistics, we talked a long time ago, is that the cluster analysis is a very important technique that's being used for separating out individual points into different groups. This is the statistical kind of subjects that is very hard to get started. But once we start, then we got to have spend the whole semester just covering that. Then graph cuts that set up the edges that's removable makes the graph disconnected, and then how much it costs to the cutting. In other words, that we say cutting in here, and these 2 separate groups, two used to be one group, but we want to take it out. So in fact, then let me go back to this idea. I don't know, this is too much for you maybe, but one in statistics that there are so many components in here. One method is top down. So initially everything is in one group, and then started cutting up. That's and the smaller. So that's the top-down methods. This is what we are talking about. Where do we make a cut? Bottom up is that in the whole graph has a X number, very large number of different groups. So individual pixel is one group. Then you started grouping together or merging together, and when it gets enough distances to be within that range, then you will make it as one group, and this one as one group. So it is more like a forming little bit of the group here, and that group grows. Sometimes they merges. That's a bottom-up method. So which method is better? Both are used. That depending on the data. Some data are very much scattered, and bottom-up maybe. But if a total picture has a pretty good grouping, then top-down is a more efficient way to do that. So what would be the best algorithm for cutting? So in the case, the distance-wise here, the minimum distance, when the distance, this one, the distance, actually distance is how far off a similarity matrix, and the similarity constant or the coefficient is 5, 2, like that, then they are close enough. But this similarity or connectivity, the distance is is only 0.1, something like that. So, okay, anything less than 0.2 will be cut. They treat it as a separate unit, then we'll do that. That's the idea about this cutting to separate groups. Then the normalized cut is that you just make a total distribution, and based on its standard deviation and how far off that you can make the separation. So ideal cut is right in here, but sometimes that you may give, if a criteria is too harsh, then you may not be able to make any separation. But if it's too loose, then you may make into all separate the segments. So even if it is one part of, say, cat's the body, but still you make separate groups. So proper the judgment or proper value setting is very important. So we have for each method normalizing cut that are based on Gaussian the distribution, that you just decide which one group. But the Gaussian again is normally distributed, so that's a well clustered whatnot. Then you just they make those separation, but depending on how the steep or how the large those value you set it up for the separation, that it may give different results. So there are quite a few different techniques for this segmentation, and this is another one. So remember that we had first one beginning with this k-means and the moving average, and we have a normalized cut. Like that one. So different the methods being depending on the type of data and the results of this calculation, you can use different methodologies. So there's a weight factor and how the expensive it is to cut it up, separate it out. That's what calculating out. So this is all the detail of those mathematics. So I'll just skipping it, but it all depends on the calculating being matrix. So all the data become matrix, and that's why I say eigenvalue, eigenvector represent into simpler the structure that will be unique for that individual is very important, and the purpose of eigenvalue, eigenvectors. So normalized cut is same idea about those the relaxing y, and then you calculate. See, this one is exactly what we're talking about. The eigenvalue, eigenvector. This original the matrix. The difference is they separate that is a vector, and the lambda is a value of eigenvalues for representing whole uniqueness. So this is the algorithm again. It's all eigenvalue, eigenvector talking about, and the result. But the good thing is that the results are sometimes very good because you are separating it out. So when you are doing those separation, you have initially detected the features. From the feature, you are trying to find the separate segments. That in here, this tiger, here's some bridge shape, and that can be very effectively separated out by those average, those cuts by this Gaussian model. Then the segment is a mosaic of a texture. There are so many different things all arranged. That's a little hard. So in the case that there's another technique known as a DB scan, that's a density-based spatial clustering of application with the noise. So this is all talked about those, in AI class sometimes for the in deep learning. So here's some separable one, density-based. So how they are dense, the distribution-wise, and then what you do is somehow that those things are not linear, then try to spreading it out by some constant value changes that's spreading into those even separation. And this one by transforming the data and then try to make a much more separable in terms of linear line or boundaries. And this gives by transforming, actually it's called a matrix rotation, by rotating a little bit. Isn't it that sometimes you look at something that looks funny, but then you turn around the objects a bit, then you see the right place to have a very nice cut. So that's the kind of idea here. So this can be. So if non-linear separation here, so you try to cut it into the linearized. Then here the convolving image with a bank of filters. So you have the changing, the multiply and convert into filtered image. Then may give much better the results of straightening your data. So this is like a filtering. Then texture. This one is a texture. So using that one is the same pattern repeating. So once you have a same pattern repeating, you try to make those pattern part as a kind of a same region. So in region we expected all homogeneous, but if what if that we have those dots or sometimes X marks as a member superpixel, just like a superpixel that we have a box of the pixels, so that one certain pattern and those things are matching, then we say, aha, this one all matches together. Then that can be transformed into different color coding like that. And the other part, this is actually arm part, is a different texture. So you can make a separation between this arm part and this cloth part. This one, contour texture analysis of a segment, is 2001, about 20-year-old the researches, but it is interesting. You can go and look at those. So the texture itself can be transformed into much the fixed, the uniform patterns. So we are having those different part, and then texture features. Sometimes that we say that this one we cannot make a distinction inside there. So same paper to keep the saying something good and bad about this methodology. So inventing contours, if I can, the connecting weights, and if you have a center of gravity, and we say this one is going up and down, that kind of relationship, it may be able to solve those ambiguity or those overlapping of the different values. So here's something we had in earlier part, that is we have different type of pictures, and we are separating of some has a texture like that, and some has just the homogeneous the kind of a texture, or homogeneous pixel values, but separating it out into different groups by different technologies. So here Berkeley University has researching on and how to make a separate segmentation being made. So you can actually visit this place. I don't know whether I can do it in this, but this link is valid. So why don't you take a look at it? And then they have a lot of research going on. So still, best segmentation, the engine takes this segmentation technique takes some more research for the more efficient and easy to understand form. And then once we have a segmentation done, so separate out different groups, then we should be able to start the labeling. But labeling also is not automatic. We can just say this is a building window, easier, but how can computer do? there gotta be an algorithm and pattern matching. That's something we may cover next time. So here's many samples that this cats and the sky and the trees and the cows and the sky and the grass here and the trees here. So just identifying separate component. So purpose of segmentation is, first of all, from the feature information, we started getting which two groups getting together. That's when we talked about k-means and clustering, moving average, like that. So grouping similar things together. But once you do that, then by the shape and some other model for the matching, we should be able to identify it as a sky and another animal and cow. Then very interesting subjects like how do you make a difference between cat and dog. They are both animals of small sizes with the ears and the nose and the eyes all together. And there's a distinct differences over here. So by looking at that, you see that's a cat or it's a dog. So that is something of needing some kind of a machine. So normalized cut is another technique, something new, but it can be useful for some identification and the labeling. And the good thing about it is that it's pretty much robust, meaning they can be used for many different situations. But the problem is it's very expensive and to calculate, and it takes so much of a storage requirement. And then if the normalized cut, actually what it is that when it's partitioned into equal sizes, that's it tries to make everything equal because of normalization process. So often that the data or often the result may be a little bit biased. And then now the segments, individual segments of this one can be template for the matching. So you have this kind of a shape, this kind of shape. Then you want to find the right matching of same objects. They're from here in the more complex pictures. So this is also very interesting subjects that to look at into pattern matching. That goes to the next subjects also. And then objects, the detection. Once we have a human pattern, then you have a general shape like that, and plus some of a shape like that, and then you get the in here. This one has a certain area being looked at it, and the shape, the foreground, the background, color model. With that, somehow there's a bright area, so it looks like these two are similar. But with the graph cuts, then you can get those separated out, and this one is a separate unit. This one doesn't do that. So in here, as you go on, this one is just a face part isolated. This one is a face part, doesn't look like, and there's so much of other component that doesn't seem to be belonging to. So this one gives higher scores. So this is the formula for segmentation for the object detection. And this one can be top-down segments. So you can have different groups. You're just separating out, and then make those separate components being added to the identification. So top-down segment is that, okay, I have one segment or one pieces that's more like a head, and another piece more like a body, another piece more like a leg, and maybe we can conclude that this is a horse, or this may be a cow, like that. So in here, that normalizing cut, and then you do the segmentation and make an identification being done.